In one of the earlier episodes, we talked about the general nature of various kinds of ore deposits and their classification. Today, I have chosen three related processes. All three of them are related to magmatic activity. The lesson will be discussed under the following heads. Sources of all metals is ultimately magma. When hot and under pressure, elements remain in solution, but sooner or later, with reduction of pressure and temperature, crystallization begins. Fractional crystallization will separate ore minerals and common rock forming minerals. Depending upon their temperature of crystallization, and early formed minerals may incorporate certain elements. Early in the crystallization history of this magma, if original concentration was more than normal, these elements like chromium may form their own minerals as oxides. These crystals, being heavier, will settle down with other common minerals and are referred to as early magmatic deposits. In general, for most of the magmatic deposits, the host rocks are mafic and ultramafic bodies, being specific all over the world. Following ore deposits, magmatic rock types association is very well recognized. Primary diamond with kimberlite and lamproite, chromite, magnetite, platinum and iron with peridotite, dunite and gabbros, titanium ores with magnetite, with gabbro and anorthosites, nickel copper sulfide with norite and corundum with nepheline cyanite, beryl, lepidolite, tin, tungsten and polysite, which is an ore of cesium, they are with pegmatite. These are perhaps the most common group of metallic deposits, including those of copper, zinc, lead, mercury and silver, and also gold and tungsten. As the name indicates, these ores were transported by hot water fluids. The temperature may range between greater than 500 degrees centigrade and pressure 1 to 3 kilobars. Their major constituents being sodium, potassium, calcium and chlorine, while several minor and trace elements include copper, lead, zinc, magnesium, boron, sulfur, tin, molybdenum, gold, silver, as also carbon dioxide and SO4. Source of heat and the driving force undoubtedly is the magma chamber. Metals could be either from the magma or the remobilized metals contents of the rocks in the surrounding. The country rock, which may be of any origin, is seldom without openings. These openings or cavities may be a depositional feature like pores of a sandstone or vesicles of a volcanic rock, or might have been produced in the rock due to tectonic activity or other factors after the formation of rock. These are called induced cavities. These original or induced openings become the favorable site for the deposition of hydrothermal fluids. Among all the processes of ore formation, this happens to be the most common type of mineral deposition and is responsible for a large number of deposits now being mined. The process of cavity filling is favored more at low pressure, that is shallow depth, and low temperature, that is less than 300 degrees centigrade. Thus, most of the deposits of the epithermal category will be of the cavity filling type. The second way involves chemical interaction between hydrothermal fluids and the country rock, whereby one or more of the earlier formed minerals of the country rock are replaced by the newly formed ore element or elements, often retaining the old structure to the very detail. The ore element content in a way is the gift of the hydrothermal fluids to the previous mineralogy of the country rock, and both together constituting the newly formed replacement deposit. The process of replacement is more favorable at high temperature and high pressure, and it should be obvious that is the way of ore formation will be more. Cavity filling in the rock is analogous to a dentist filling a tooth cavity and is by far the most common process of ore formation. Layers after layers of minerals in a symmetrical way, making a comb structure. Several types of cavity filled deposits have been recognized, as will be seen in PowerPoint 3. Igneous and sedimentary rocks will have different types of openings, which will become sites for mineral deposition. To name few: stockworks, saddle reef, ladder veins, breccia fillings, pore spaces, bedding planes, vesicular fillings are some of these. Among these, fissure veins is by far the most common tabular or sheet-like body in shape, generally discordant, opening in rock, and a very favorable site for ore deposition. These may be simple, composite, chambered, sheeted, and are source of many of the ores and mineral deposits of the world. Different types of cavities and fissure veins are illustrated in PowerPoint 4. In the Indian context, Singhbhum shear zone deposit of Jharkhand, which is a copper uranium deposit, is perhaps the best example of shear zone which is connected thin sheet-like openings in a zone of ductile deformation. Deposit some of the world's most famous names in metalliferous deposits are cavity filled, mostly fissure vein type of deposits. For example, Mother Lode of California, also those of Kalgoorlie, Australia, Saddle Reef gold deposits of Bendigo, Australia are just a few of them. Kolar and Hatti goldfield of South India are also fissure veins and shear zone deposits of this category. The famous Champion Reef lode has produced more than 850 tons of gold. Unlike cavity filling deposition, which takes place at temperatures which are lower, metasomatic replacement is the most favored process of ore formation at elevated temperatures and pressure conditions. Hypothermal and mesothermal, that is, and it is a volume for volume transformation. However, it is not always easy to draw a line between cavity filling and replacement deposits. Often, wherever a large size cavity is being filled, metasomatic replacement is a rule rather than exception. All hydrothermal deposits may not possess regular shapes and forms as described above and illustrated in PowerPoint 3 and 4, but may get disseminated, sprinkled in a layman's language, in a large plutonic body, much like pepper sprinkled on a food item. Such deposits will be extremely large, though of poorer grade. Porphyry copper deposits come under this category. Presently, more on this very interesting theme is outside the scope of this lesson. Yet, another recently developed concept of hydrothermal ore deposition is in short referred to as VMS deposits, that is volcanogenic massive sulphide deposits like that of Cyprus at constructive margin and those of Kuroko, Japan, island arcs near the destructive margins. These are mainly sulphides precipitated from the hydrothermal fluids which we called earlier black smokers and white smokers, emanating from the seafloor vents and deposited along with the seafloor sediments in an ophiolite setting. Details of this important mechanism of ore deposition, which is presently going on in the oceanic environment, is beyond the scope of this lesson. Extent wise, these deposits may be irregular, small, but rich in grade and develop at the contact of a magma with a reactive rock. Their depth of formation may be around a few kilometers, while temperature range being 350 to 800 degrees centigrade. Skarn is not the only name for these deposits. They have been called by other names including hydrothermal metamorphic, contact metasomatic, pyrometasomatic. Originally, the concept was developed by Finno-Scandinavian geologists. There are a number of characteristics attributed to this kind of deposit. Number 1, they develop around magmatic bodies like dikes, sills, lopoliths, porphyry stocks, and within the contact of rocks that are preferably reactive. Second, these are more common in intrusive rocks of intermediate composition due to the presence of more water and volatiles in them. Granite limestone contact has better chance of developing into a skarn than basalt limestone. Third, reactive rock type like limestone and dolomites, as these will react with the chemically potent fluids rich in chlorine, fluorine ions, are more easily affected than a non-reactive rock like quartzite. An intrusive which is in contact with a shale will have a better chance of hosting a contact metasomatic deposit than a sandstone for the same reason. Fourth, the principles of ore minerals fall under two categories: the oxides, mostly that of iron, tin and tungsten, and the sulphides, that of copper, lead and zinc. According to the temperature of formation for these two groups, it should be expected that the oxide ores should be nearer to the contact due to higher temperature, while sulfides farther away, whereas the middle part is dominated by calcium magnesium silicates, especially garnets, as shown in PowerPoint 5. Number 5. Among non-ore minerals, there is a characteristic development of a number of calcium and magnesium silicates, including wollastonite, lime garnet like grossularite and andradite, epidote, serpentine, zoisite and albite. Among the gangues, quartz and calcite are common, while tourmaline and topaz are also not uncommon. Sixth, since carbonates are the most favorable hosts, their detailed mineralogy from known deposits across the world has been worked out by a number of scientists. This has highlighted the importance of limestone alteration zone known as Skarns. Gradual change in temperature, pressure from the contact outward yields a distinct assemblage of different sets of ore and non-ore minerals known as mineral zoning. Cornwall County in the southwest of England has been a celebrated area for the understanding of such types of deposits, especially the ore mineral zoning. A simplified diagram makes this clear as shown in the PowerPoint, where the contact between the invading Paleozoic granite and the carbonate country rock has resulted in a number of oxide and sulfide ore minerals in the skarns as shown in PowerPoint 5. Indian examples of this type of deposits includes barite deposit of Kadapa, which is at the contact of limestone basic rock, which is a sill. Wollastonite of Rajasthan, as also Sirohi wollastonite can be another example, as also graphite occurrences in khondalites of Odisha, magnetite bodies of Visakhapatnam, Andhra Pradesh is another example. A number of important contact metasomatic deposits of the world have been presented in PowerPoint 6. To summarize the whole lesson, magmatic concentration, contact metasomatic skarns, that is, and hydrothermal deposits are three of the most important mechanisms of ore formation. All three of them come under the broad category of deposits formed by internal processes which operate under high temperature, pressure environment. Magmatic deposits mostly consisting of oxides ore of chromium, titanium as also sulfides and diamond can result due to segregation, immiscible liquid segregation injection either in the early or late stage of crystallization history of the magma. Ultramafic and mafic rocks are the obvious hosts, and there are clear association of specific ores with specific rock types. Contact metasomatic deposits result due to give and take relation between the igneous constituents, that is heat, ore elements and volatiles, and the invaded country rock. Hydrothermal solutions are intimately related to magma and are charged with sodium, potassium, calcium, chlorine and several minor and trace elements and dissolved gases. With decreasing pressure and temperature, they get precipitated into available spaces by processes of either or cavity filling and replacement or both. Depending upon the temperature, pressure of deposition, they are termed hypothermal, mesothermal, epithermal, telethermal or xenothermal deposits. Two special kinds of hydrothermal deposits are the porphyry copper deposits, which is developed in a granitic host rock, and the volcanogenic massive sulfide deposits developed along the constructive and destructive plate margins. In a nutshell, magma thus is not only the parent of common igneous rocks, but also the provider of much sought after economic ore minerals in more than one way. I hope you have learned something about these three very important mechanisms in which we find ore deposits resulting directly or indirectly from magma.